Hello, Flat Earth researchers, debaters, and debunkers. How on earth can we look at a sunset like this and say it's because we live on a spinning globe Earth? If we're honest with ourselves, we cannot say that we know it is true that we are on a globe. In fact, our senses tell us otherwise. The only reason we believe it to be true is because of what we've been repeatedly told since we were kids, to imagine ourselves on a globe. But anyone who comes along and tries to tell you that they know for sure that it's a fact because of science that we live on a globe is not being honest with themselves, and they're not being honest with you. In fact, the entire heliocentric globe Earth model was imagineered not by measuring any curvature across the surface or detecting any movement of the Earth. It's all been created as a mathematical model by looking at the sun rise and set. And a decision was made a long time ago, before people could even get high up into the sky, to put the sun at the center of our solar system, to create a Gregorian calendar that tracks time and measures time throughout the year or over the years by having the sun at the center of this calendar, when in fact there are many, many ways we can measure time. We can have a lunar year and it all works out to be the same. But we've been told that this Gregorian heliocentric model is a scientific fact, when the only way that this can be reproduced as a mathematical model on paper in 2 dimensions is by taking away that 3-dimensional perspective that we have and turning it into an imaginary curve on paper. So let's have a look at perspective. We're going to have a look at the sun, the moon, and the stars, especially Polaris, and how that has been used, or how perspective is the reality of what we see and how it has been ignored or replaced with an imaginary curve. Here's an excellent example of perspective. We can see straight away that these railings, although we know they would be parallel to the surface that we're looking across, and that it's a relatively flat, although uneven surface, these lines, these parallel lines, appear to sink towards the horizon created by the surface because of perspective. So this is the kind of view that we always have across the Earth. It's always from a very low perspective. And we know that perspective causes anything above our eye level going off away from us in a parallel line to our line of sight will appear to sink towards the center of our field of view. And that likewise for anything that's below our line of sight. So this floor is below the line of sight here and appears to rise up to the eye level somewhere in the center. So we have this very kind of extreme declination of perspective, the angles of perspective here, because we are so low to the surface. Of course, we know that if we have a side-on view of railings on a pier like this, then those parallel lines will never appear to meet. This is how they are in reality. So we can now realize that when we have a view like this, that what we see is parallel lines that never actually meet, they only appear to meet. So we can, for example, illustrate the sun making its way across this image in a kind of parallel direction to the railings or to the surface here. But if we were on the surface and the sun was above us, we know that it wouldn't appear to maintain this consistent height. Here we'll just show how the railings appear to be and the floor. If our line of sight is right here, in line with this middle railing, if we were on the pier, looking down along it this way, those railings would appear to sink down towards our midway point in our field of view, and the floor would appear to rise up, although we know this isn't physically happening. So we know that parallel lines going off into the distance, or something parallel to our line of sight going off into the distance, is going to appear to converge in the distance, in the center of our field of view. This is perspective and how it works. So if we just take this further and illustrate what we would be seeing if we were stood on the pier right here, where that seagull is or something, what we would see as the sun goes off into the distance, maintaining a constant height above the surface, is the sun appearing to follow this line of perspective and meet somewhere in front of us with the surface. That's what it would appear to do. Of course, we know it's not doing this, but this is the only way we can illustrate this, what the observer sees from this side-on perspective. As perspective we never have of ourselves, because we can only see through our own eyes. So we can illustrate this in this way. Back on the pier here, with a sun following these lines of perspective created by the railings here, and we would see the sun eventually meet with the floor. Now, people will argue about angular size and demand that the sun changes in angular size as it gets further away, just as we see the railings appear to get smaller and smaller as they go off into the distance. But isn't this a ridiculous thing to demand when we see these physical, tangible railings in front of us and this floor, a very short distance in front of us, maybe 100 or 200 meters, converging in the distance? So why should we expect the sun, which is an intangible light in the sky that lights up entire continents, why would we expect that to change in angular size at the same rate as we see this change in angular size due to perspective right here in front of us? That's just ridiculous. It's demanding the impossible. As the sun goes off into the distance, it's going to appear to hit our horizon and converge in the center of our field of view. And of course it will get cut off by the surface as it doesn't actually physically go down, it just continues off into the distance but appears to sink. It's perfectly acceptable for it to be doing this above a flat Earth due to perspective without changing significantly in angular size, because the distance that we can see across the surface before the surface cuts off the sun is relatively short compared to the distance the sun is going in the transparent sky. Here's just a lovely example of that. Now, we're told that we live on a globe Earth, and we have a North Pole that's pointing in a tilted direction, looking up at the star Polaris, somewhere up in the sky. And the Earth is tilted at about 23.4 degrees. It varies, 22.5, 23, 24, 25 degrees. It's arbitrary. It's very difficult to have this calculated or measured very completely accurately. So we're told that the equator is actually tilted, and this tilt and spin of the Earth is what causes the seasons as it orbits the Earth in this direction, horizontally. So let's keep this figure in mind, 23.4 degrees. It's basically half of 45 degrees. So yes, we have 90 degrees here between the equator and the North Pole, and then the angle between these two is 45 degrees. So this is basically half of that 45 degrees, this alleged axial tilt. So this is what we perceive is happening. I'm not advocating any particular model here, just to say that it's perfectly acceptable to perceive the sun doing concentric circles throughout the year above a flat Earth. We do not know the dimensions of that Earth, and it doesn't mean it's floating in space. This is just to look at what the sun's doing throughout the year. So in the winter it's doing a wide circle around the North Pole. In the summer and spring it's doing tighter concentric circles and then going out again as the winter comes around again. So this is the concept. Again, it's not a view we've ever had of the Earth to prove it either way, just like the globe. But we can see how this is perfectly feasible and possible when we factor in the laws of perspective. So this is the kind of thing you would see if you were, for example, on the inside of the circle. Now, this may look like we are on the outside of a circle. If we just go back to this a second, if you're south of the equator, then you're going to be outside this circle here. Obviously, if you're north of the equator, then you're going to be inside the circle. So you would maybe perceive that we would see this arcing across the sky that would show us we are either inside or outside of the circle. But when we factor in perspective as well, and we consider the massive size of the Earth and what the sun's doing, then we realize that this kind of view is actually because we are on the inside of the circle. And again, the laws of perspective are dictating what's happening here. The sun over here is very far away. As it gets closer on its circular path, it will be at a point where it's closest to us, even if we're on the inside of the circle, and it will appear to be high above the horizon. Of course, if we are at the equator, then the sun goes directly overhead. But if we are away from the equator, then we'll only see the sun arc across the sky, simply appearing to get higher in the sky because it's getting closer to us, and then appearing to get down towards the horizon again because it's getting further away. So we could be on the inside or the outside of this circle that the sun's doing when we see it like this. Yeah? So we can just use this picture here to illustrate this. Of course, we can see perspective at play on the surface here. Everything appears to converge in the distance at the horizon. And this is a view that we would never actually have across the surface of the sun. Although this is what we can perceive is happening. The sun's going across the surface but maintaining a consistent height. But again, because of perspective, the further away it gets, the lower it will appear to sink towards the horizon. The higher it gets, then the more it will appear to rise to the horizon. And this is the kind of view you might have of the sun as it sets, goes off into the distance, and appears to get cut off by the horizon. Again, no need to demand that there is any change in angular size of the sun, because it's getting cut off very early by this very short view across the surface. The sun is in the sky going away from us. It's a lot further away than anything on the surface that's cutting it off before it gets very far away. And again, we can have this kind of view. So this may be, we could be in the north, in say the UK or Europe, looking south. So east is over here with the sunrise in the morning, and as the sun gets closer, it comes up above the horizon. And again, we could be on the inside of this circle, but this is the effect we would see due to perspective, because there's going to be a point where the sun is closest to you, and that will be your midday, and it will be highest in the sky. Again, it's not going to go over your head, it's going to arc across the sky. So going from east to west, this is how you would see the sun behave in somewhere like the UK, looking south. What I've done here is added little dots to represent sunspots. This is an observation I made myself, both in Thailand and in the UK. Lucky enough to see sunspots in both those places and see how the sun appears to behave. And what it appears to do, if you're in the north of the equator, is the sun appears to rotate in a clockwise direction as it makes its way across the sky. It appears to be rolling across the sky. Now, it's very, very difficult to try and model this on with a globe Earth model. Almost impossible, I'd say, but we can do this ourselves and model it with a flat surface and bringing something towards us and then having it go further away on a circle. This is the kind of effect that we get when it's the sun that's moving above us and the Earth is stationary. And what you'll notice if you watch the sun and moon is that they both appear to follow very similar paths. Okay, we've noted that the sun will change its circular motion throughout the year, apparently getting higher and lower in the sky, creating the seasons, and we'll come back to that axial tilt in a minute. But essentially, if you watch the moon from any given location and you're fortunate enough to see sunspots on the sun, you'll notice that the sun and the moon appear to rotate and roll across the sky in exactly the same way. So this to me says that we are not in a position where the moon is orbiting us and we are orbiting the sun. Both are above the flat Earth, rolling around above us. While we're on the subject of the sun and the moon and making predictions of celestial movements such as eclipses, the heliocentric model has no ownership or precedence of being able to make predictions of eclipses. These are things that have been predicted for thousands of years by all kinds of cultures, none of which used a globe or a heliocentric model to make their predictions. In fact, most of them use a lunar calendar. And we can see from the observations we make that the idea that the Earth is a globe and spinning and that the moon orbits the Earth only once a month or once every 28 days or so, and that the Earth is spinning to create day and night, is just one interpretation from, again, looking up into the sky, not seeing any measurable curvature across the surface of the Earth, not seeing any kind of spin whatsoever on the Earth, simply by looking up at the sky and using the sun and moon rather like we look at the hands of a clock. So again, all that's ever been done with any particular model is to tell the time by looking at the big cosmic clock in the sky. And it just so happens that the heliocentric model is focused on telling the time with the sun, whereas you can use a lunar calendar in exactly the same way, and we could all make stories as well about the sun, the moon being at the center and having mass to pull everything towards it. Wouldn't know any different. We could just make up all these stories about it. But none of these other cultures have ever attempted to tell the time by looking up at the sun, moon, and stars, and then try to explain that as being our physical reality. So there are cultures and countries on the Earth that use a mixture of the sun and the moon and the stars to tell the time throughout the year. It's just a clock, and it has different moving parts. But the Earth certainly doesn't have to be one of those moving parts. So what we can see, again, this is an illustration that doesn't include perspective, it's just to illustrate the point that we can look up into the sky and we can see that throughout the month the sun is moving at a faster pace than the moon. The moon moves at a very steady pace, and this again works out throughout the year to become the same length as about the same length as a year for the sun. So it doesn't matter which one you choose to put at the center of your model. You can still tell the time and make predictions. So what we'll see throughout, I'm just going to illustrate what happens throughout maybe a few days, 5, 6 days in the month. And you can just go outside and make your own observations. But what we'll see is we'll have, I suppose, what would be a fairly new moon, because we've got the sun coming up here. So this is at some point in the morning. The sun is in the east here. Remember, we're looking south. So the sun has come up in the east, and it will be quickly followed by the moon in this particular illustration. And the next day, what will happen is, let's say it's about an hour later, for example, until we see the moon in the same spot that we saw it the day before. So the sun has already progressed, so it's later in the day, because it's gone on, we can see that the sun has moved on, it's later in the day now, and only then do we see the moon come up later on. And then the next day, the sun and the moon are further apart. So the sun, we don't see the moon in the same spot again until the sun has progressed further along in the day. So let's say it's more towards midday now until we see the moon rise in the east. And so it goes on. The next day, it's coming towards the afternoon now before we see the moon. And this is why every month you can predict when you will see the moon in the sky in the daytime or in the nighttime. Yeah? Okay, and again now it's the afternoon, late afternoon for example, and it's only then that we see the moon rise, simply because the sun is moving around in its circle above the flat earth at a faster rate than the moon. The moon's going a steady pace, so in the course of a month the sun laps the moon, as it were, and comes around again. So the next day they're even further apart until halfway through the month the sun and the moon are opposite each other. We get a full moon, whether it's in the daytime or the nighttime, that we see the moon, and then it carries on going, the cycle continues, and the sun and the moon get closer and closer together again until we cannot see the moon because the sun's in the way. Yeah? So, and the sun and the moon may be, they'll be following similar paths, but one may be higher or lower than the other in the sky. And this is how we can make predictions for eclipses, because we can see throughout the months as they progress that the sun and the moon's paths will eventually cross. And we can make these predictions without any presumption that we're on a spinning ball, just by looking up at the sky and telling the time by comparing the movements or the observations of the sun and the moon. Okay, it's as simple as that. So let's have a look at how observations of celestial objects are used to navigate across the Earth. This is an instructional video that will explain how to use a sextant observing Polaris to determine your latitude. And of course it assumes a globe Earth model. But in fact you can also assume a flat Earth and it works perfectly fine in exactly the same way. The only difference is that the globe Earth assumes that the surface is curved, and this makes Polaris appear higher or lower above the horizon, whereas on a flat Earth it is perspective and your distance from Polaris that determines whether the star appears higher or lower above the horizon. Both work in exactly the same way. Now, just to illustrate the point here, it is always assumed, it's a given, that the horizon is at the observer's eye level. So the measurements start from the horizon up. The angles are measured from the horizon upwards. So the horizon is your starting point, which is always at the observer's eye level. And here it already assumes a flat surface. And we know that if we were closer to the star and the star was local and traveling across a flat surface parallel to the surface, that's the closer you got to the star, the higher your angle of elevation would be to observe that star from the horizon. We also know that the further away you get, due to angular size and perspective, the star would appear to drop down towards the horizon the further away you got, just in the same way that we observe a row of streetlights appearing to sink towards the horizon, even though they are parallel all the way along that row to the surface. So let's listen to what they have to say, and we'll stop it at a couple of points.
So what you would do is you would go out on your ship at night, and you would use an instrument, such as an astrolabe or a sextant, and what you would do is you would find Polaris in the night sky, and you would measure how many degrees Polaris was above the horizon. Now that number of degrees is really important because it turns out that the altitude of Polaris, or the height of Polaris, is equal to an observer's latitude. So if you observed Polaris 48 degrees above the horizon, it meant that your latitude was 48 degrees north.
Okay, so it doesn't matter how high in the sky or how far away Polaris actually is from the North Pole, above the North Pole. What matters is how far away you are from it. So if Polaris is local and you get further and further away, it's going to appear to sink to the horizon. And this will determine your latitude. So the latitude lines on the Earth, flat or round, are determined, or were determined, by the position of Polaris above the horizon. That's how these latitude lines were determined in the first place, based on these observations in the sky above the flat horizon, not by measuring any curvature on the surface. Okay, so Polaris is an intangible object, and observations of things in the sky are determined by perspective. So let's carry on. So just to emphasize that this works with a globe model, but it also works on a flat Earth. On the globe model, you assume the Earth's surface is curved. On a flat Earth, you incorporate the reality of perspective, which determines and governs any observation that we make.
The reason it works that way is because Polaris is located right on top of the Earth's axis. But it's so far away that when light from Polaris gets to the Earth, it basically is all coming in from the same direction because Polaris is so far away.
Okay, so this idea that Polaris is so far away isn't something that's ever been physically measured. It is just an assumption that has to be made because you assume a globe Earth model. But it turns out that looking from the surface of the Earth, in this model, Polaris can be here, 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 or here. And they talk about it just because the light from Polaris appears to come down here. So they're not even referring to the physical position of Polaris in relation to the Earth. They're talking about where it appears to be. And you'll see how they actually assume a flat horizon at the same time.
So if you're standing at the North Pole and you want to see Polaris, you're going to look straight up over your head. So if we measure the angle that's formed between the surface of the Earth and straight up over your head, well, it's a right angle. It's a 90-degree angle. Well, the latitude of the North Pole is 90 degrees north.
Okay, so that's fairly straightforward, straight up towards Polaris. And again, we've assumed that the surface is flat and the horizon that you're looking across is also flat, perpendicular, so you get the 90 degrees. So, of course, the latitude lines of the Earth go down, 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 90, 80, 70, 60, 50, 40, 30, down to 0 at the equator. And then, of course, it starts again. And of course, it's assumed that it is the curvature of the Earth that blocks your view of Polaris. When in fact we know that across a flat plane, if Polaris is very local, then of course you'd get exactly the same optical effect.
They're the same. If you were to travel a little bit to the south, let's say you were located over here, well, now we can see that here's the horizon, here's the surface of the Earth. If you want to see Polaris, you're not going to look straight up over your head. You're going to look this way. And so there's a much smaller angle. Maybe that's around 45 degrees. So maybe.
Okay, so again, they have to assume a flat surface, a flat horizon at the observer's eye level, despite this curve. So they're not making an angle that leads directly to Polaris. They are making an angle that goes from the observer's horizon, their eye level, and then up to where Polaris is apparently visible, which is here along this line of sight. So what's happened is you've got this assumption that Polaris can appear here, 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 or here, even though physically it is said to be here, and a flat surface and your angle of elevation from that flat surface. So the difference here really is the angle of perspective, or that angle of declination that you would get across a flat surface, rather than assuming that you see the star here, even though it's physically supposed to be there. So you're getting the same declination that we see due to perspective across with a star traveling across parallel to a flat surface. Let's just listen to the end of this.
Maybe your latitude is 45 degrees north. If you continue going south, let's say you go to the equator. Well, the horizon, or the surface of the Earth, is right over here. Straight up over your head would be over here. So Polaris is clearly not over your head. Well, Polaris is basically the same direction as the horizon. So in other words, there's no angle. It's 0 degrees.
Okay, so hence the equator being called 0 degrees. But you can see what they've done here. They assume that your line of sight to Polaris is over here, not where it is physically supposed to be over here. Again, ignoring perspective. So it's the same as being going across a flat plane. And here we can see that they've again assumed a flat horizon at the observer's eye level. So they're saying that Polaris has basically met the horizon because it has declined to the horizon. Again, this is just a natural phenomenon observable due to the laws of perspective. Here's another illustration that clearly shows the contradictions that have to be made if you assume that you're on a curved surface. Again, we have this line of sight, the eye level horizon, as the starting point for measuring the angle up to Polaris, which, although is a speck of light that is supposed to be physically placed above the North Pole, it appears for this person here to be up here, and for this person over here to be up here. These are thousands of miles apart or distant from the North Pole, and we have to make this conjecture to compensate for the idea that we're on a globe. This one shows the same thing. Again, we have the eye level horizon ignoring this curved surface. Okay, so the measurements are taken from the eye level horizon, a flat horizon, up from there, and here it says the light rays from Polaris are parallel when they reach the Earth. So again, even though Polaris is supposed to be a speck of light in the sky, physically placed above the North Pole, it is assumed that depending on your location, you see it here or here or here or here. Okay, this really is obviously something that can only be illustrated and assumed in this globe Earth model, cannot be physically demonstrated to be a fact. Again, compensating for perspective, the angles of perspective that make things decline towards the horizon. And this illustration shows the ridiculousness of the assumptions and calculations, not real measurements, that have to be made to assume that Polaris is 3.6 quadrillion kilometers, or 400 light years away from the Earth, and that the Earth is 300 million kilometers from the Sun, just to fit the idea that the Earth is moving or orbiting around the Sun, and Polaris doesn't appear to move in the sky, despite us being hundreds of millions of kilometers away from the Sun. Again, this is not any kind of measurement. It is just calculations that have to be assumed in order to fit the globe Earth heliocentric model. So what's important to keep in mind here, that we have two branches of mathematics that are different but also similar to define the globe and to navigate across the Earth. The globe, of course, uses geometry, and it's divided in two at the equator, so you have two hemispheres. And if that's represented in a two-dimensional view, then you have two semicircles, which, of course, from one side to the other is 180 degrees. And again, with trigonometry, which is used for making observations and measurements of the height of something above the surface, then we also are using triangles that have angles that add up to 180 degrees. So these two branches become interchangeable. For example, we know that when we have a triangle like this, so we create a triangle with an observation. If we look directly up at something, or this side here of the triangle, the vertical side, can represent the height of a tree or a tower or something above the Earth. And if we have a distance across the flat surface that is equal to this height with this right angle here, we then have an angle here of 45 degrees. So this is when we can use surveying and trigonometry to estimate or calculate the height of something above the surface based on this side, this vertical side, and this horizontal side being the same length and giving us an angle of 45 degrees right here. So, for example, when the sun is shining on something at 45 degrees, then we get a shadow that is exactly the same length as the height of the object and an angle of 45 degrees. Once you get further away, or you make this triangle longer, sleeker, then this angle changes, of course. So it's after that 45 degrees that is important and where perspective kicks in. So let's have a look at how observations are made in reality on the surface of the Earth, and how trigonometry and angles are involved. Now what we have here is this person looking at a tree, the observer. Okay, so we're going to represent what the observer sees, and the horizon for the observer is at his eye level. Okay, so when he looks at the top of this tree, there is an angle between the surface and the top of the tree. And again, if he is at the same distance from the tree as the tree is high, we have a right angle here and a line of sight to the observer. Okay, so what we then get is a 90-degree angle here and two 45-degree angles here. Okay, so it just so happens that this is how it works out. When we have 45 degrees here, 45 degrees here, 90 degrees here, we get a total of 180 degrees in this triangle that is formed. And we know then that the distance between the observer and the tree is the same as the height of the tree. So this is the very simple way we can work out the height of something without actually climbing up the tree and physically measuring it with a tape measure. Okay, and this is fine when we know how far away we are from the base of the physical tree. Okay, and again, if the sun was shining down at an angle of 45 degrees here, it would create a shadow that was exactly the same length as the tree, extending right up to the observer. And again, we would have this, so we would know again that we were at a distance that is equal to the height of the tree. Okay, so this is fine. But what happens when we have a tree, or the same tree, okay, keeping in mind that this tree is still the same height, but to the observer, it's going to appear much, much smaller. So let's say it's twice the distance away or more, and will appear smaller. So, of course, what we then get is, we then get a line of elevation, an angle of elevation that is much, much less than the 45 degrees we had in the first place. Yeah? I'll just take that triangle away as well. Okay, so the angle of elevation to this tree, even though it is physically the same height, what we're doing here is representing what the observer sees. And again, remember that the globe Earth model is based purely on observations in the sky. There has never been any physical measure of any curvature on the surface. Okay, it's always the curvature is assumed from making observations in the sky. But we can see here that the simple fact that something is further away makes it appear much closer to the horizon, or shorter perspective, angular size, whatever you want to call it. This makes a difference to what the observer sees. Okay, so of course we can carry on adding. We've got again the same tree, further away, and so of course the line it gets the angle of the altitude of the angle from the horizon gets much shallower. Okay, let's just add okay, and again, so we can just represent this. Going off into the distance. Okay, so the same tree, again, the tree we know is physically the same height. So if we wanted to represent it at the same height, we could. But here we are representing what the observer sees. And another thing to point out is that the base of the trees will also appear to rise up to the observer's eye level. Again, this is a fact of any observation that we make, that the horizon will be at the observer's eye level, and everything on the surface, as further and further into the distance, will appear to rise up to the horizon. So just as the top of the tree appears to come closer with a lesser angle to the horizon, the same thing happens to the base of the tree. Again, all because of angular size. Okay, so all of this surface between the observer and the very distant tree now is appearing to rise up to that observer's eye level because of the difference in angular size or perspective. All right, so I'll just turn off those lines there, and we can do the same with the sun. The sun is here. We have a very high angle of elevation up to the sun. Maybe it's just past midday or something, so the sun's gone overhead and it's traveling off into the distance. So what we can show here is that we know in this model, per se, that the sun maintains a consistent height above the surface. And if we were to draw a line from the observer to that sun, then okay, in this kind of side-on view, that would make sense. But here we are representing what the observer sees. So we get an angle, we get a sun that appears to be down here. So the angle is different. Okay, we're not going to. This angle to the sun up here is not going to happen for the observer. Okay, the sun in the observer's eyes will appear lower than it actually is. Okay, so we just continue that. Okay, so we have again the sun appearing to sink towards the horizon, even though it actually maintains the same height above the surface. And so we have these angles of elevation for the observer which get closer and closer to the horizon across a flat surface. Okay. So this is why people who try to debunk the flat Earth get confused and get it wrong. They are using the same methodology as is used for the globe Earth model and applying it to the flat Earth model, for want of a better word, when in fact the globe, as we see here, the curve represents perspective. But in this kind of example, where they show that you get these varying angles to Polaris, they're not including perspective, and they're not including the curve. So they imagine that they have debunked flat Earth because we get these different angles. But again, they're not representing the fact that we are talking about observations made in the sky above the surface, in which perspective or angular size governs those observations and actually makes something in the sky appear closer and closer to the horizon as you get further and further away from it. Okay, so they assume that the sight lines should all cross at the position of Polaris, but they don't on flat Earth. Flat Earth model is wrong. No, they're confusing. They're trying to use globe Earth modeling with the flat Earth model. So again, the flat Earth is a model of being on a flat plane, making observations that incorporate the reality of perspective. Whereas the globe Earth takes the reality of perspective and converts it into a curve beneath our feet. And again, we can see here very clearly that even these angles of observation that they claim to be made on a globe use the assumption that we're on a curved surface, yet the angles of elevation are made from a horizontal line of sight from the observer. So even in the globe Earth model, they assume that the horizon is at eye level, which it is in fact true. But when defending the globe and trying to debunk flat Earth, have to say that the horizon doesn't rise to eye level, even though they use it in their own modeling. Yeah? And again, we've got these this looking up at Polaris in different positions when Polaris isn't physically in these different positions. They're just telling us that it's because of the light from Polaris spreading so far. This illustration is often used in attempts to debunk the flat Earth, but it's wrong, as it tries to incorporate the modeling method used for the globe into a flat Earth model, but doesn't compensate for perspective, as we saw just now with the trees and the sun. As we get further away from something, it should appear to get closer to the horizon across a flat surface. But here we have all these angles of elevation going to a single point above the flat Earth in this orthographic view, which, okay, may be physically true, but does not truly represent the observations made by an observer on the surface. Remember, we're talking about the observations into the sky that are made. We're not actually talking about any measurable curvature on the surface. So, in fact, what we do have is a matchup here of 45 degrees latitude and an angle of elevation from the eye level or horizon of the observer to Polaris, 45 degrees at 45 degrees latitude. So we can in fact assume that this may well be correct. The distance from here to here, directly underneath Polaris, would be the same as the height of Polaris above the flat Earth, 4,989 kilometers or 3,100 miles. But of course it doesn't appear to work out in this particular orthographic view because we're not compensating for perspective, which should make Polaris appear lower and lower towards the horizon as we get further and further away. So this does not debunk flat Earth because it's not incorporating the reality of perspective that governs any observations that we make, but does in fact match up to the 45 degrees. The same thing is done with the sun. Again, this is an attempt to debunk flat Earth by showing that the angles this time of course we have the sun above the equator, and we have angles that do not appear to match up in this orthographic view, again not compensating for perspective. So for example, you get here they've got the equator over here, over here as well. So yes, the sun should be directly above you at the equator, but the further away you get, so here we're going this direction to get to the North Pole, and by then the sun, if you factor in perspective, will be much, much lower, will appear much, much lower to the observer. Again, we're talking about observations made, so what the observer sees, but this orthographic view doesn't truly represent what the observer sees. It's just ignoring perspective. So let's have a look at the kind of results we get when we use this orthographic view and we factor in the reality of the observer's perspective, which makes things in the distance appear to get closer and closer to the horizon as we get further away. I've got a protractor here, which we can move about. Okay, so we have our latitude lines and a vertical line representing where Polaris should be somewhere above here. So if we take this to the 45 degree latitude line and we then draw a line that is 45 degrees, we should get something like this: 10, 20, 30, 40, 5 degrees. Difficult to see here, but it puts Polaris about there. Okay, so we can add another layer, star. Okay, and we'll plonk Polaris right there. Okay, so there it is. Let's shift that up. All right, so this is where Polaris actually is, if these are all correct in the first place. Okay, so what we would then do is, for example, at 30 degrees latitude, we then go and draw a line that is, we'll just make that, oops, .30 degrees. So 10, 20, 30 gives us a view to Polaris that is down here. Now this fits fine with perspective because we got further away than the 45 degrees, then Polaris will appear to be lower in the sky as we get further away. And we can just carry on doing this all the way through, but I have done this already, so let's just take this away, and these are the results that we get when we draw a line that is an angle equal to the latitude every 5 degrees of latitude. we get this wonderful curve. Okay? All leading up to, once you go beyond 45 degrees, they get closer and closer and closer to the actual position of Polaris. We don't have much else going on here. Certainly a lot less than we had to compensate for when we were looking at it in the globe Earth view, with the view of Polaris thousands and thousands of miles apart. Okay, so what a lovely curve we have here. And this is simply the result of factoring in perspective. And this is why perspective is the imaginary curve. We now have no need for a curve on the surface. The curve is in our perspective. As we get further and further away, Polaris appears to sink towards the horizon. Yeah, so by the time we get to 10 degrees latitude, just up from the equator, north of the equator, then Polaris appears to be down here, due to perspective across the flat plane. Yeah? And this is the math magic that has been used to make us believe the physically impossible, that we're on a curved surface, when in fact it doesn't have to be that way at all. You can have a flat Earth model with a curve that is actually in perspective rather than on the surface. So again, this is why perspective is the imaginary curve. I want to show you something very interesting here. If we take this to south of the equator to about minus 23.5, okay, so remember the axial tilt of 23.5 or 23.4 degrees. It's difficult to get it exact in this view. I'll try and get it as close as possible, so 21, 2, 3 and a slight bit, okay, and then we draw in some more lines, or draw in another line. We'll change the color just to make it stand out. So we're now at minus 23.4 degrees latitude, south of the equator, as much as we can get. And, oh, let's do it the proper way. When we aim at Polaris, we get an angle that is actually very close to the actual latitude, okay? If we actually put it up there, it's 25, so I'm just going to put it around there, okay? This isn't the most accurate software, but it just shows us that between the equator and minus 23.4 degrees, the same degrees that we are told is axial tilt, creating a celestial equator, which is the horizon that we actually use for astronomy or using a sextant. So again, this is the horizon that we use at eye level, the celestial equator, which we are told is 23.4 degrees from the actual equator on the globe. And we draw this angle to Polaris, we actually get an angle of 23.4 degrees. Again, these models that we are all told to believe in, or the globe model, is simply the manipulation of mathematics and a preference to use geometry rather than trigonometry, or a mixture of the two. Yeah? It's just math magic, playing around with numbers. And with this, we can see that it works fine. And so we don't have a dome either. Our dome of is this curve of perspective, okay? So what we are talking about here for a flat Earth model is a flat surface, and the sun, moon, and stars all in layers that are parallel to the surface. And it's only because of the observations that we make in the sky that create this appearance of a curve or a dome. So when we talk about a dome, it's a dome of perspective. And this, again, is just representing half a hemisphere. Okay, so we've got the, this is just one side, the equivalent to one side of the globe Earth, from the equator up to the North Pole. Okay? Yeah? A semi-sphere, if you like. But this sphere, or the dome, is one of perspective. So everything is parallel lines. It's like the flat Earth is like a sandwich. We're in the middle of a sandwich. We're on a flat Earth, and we have the sun, stars, and moon on a flat plane above us. And because of perspective, they appear to sink down towards the horizon in a curve. Okay? So there you go. The flat Earth model can be represented in this way when we include the reality of perspective that governs all our observations. I really hope that makes sense. And so there should be no need for anyone to argue that the globe is a fact. The globe is just an abstract mathematical interpretation of the observations that we have made of stars and celestial objects. And the lines of latitude that are drawn and turned into a globe Earth work perfectly fine on the flat Earth when you factor in perspective. Thank you very much.